Day we were talking about circular motion. We had this concept of uniform circular motion. Zach, uniform circular motion means you're accelerating, but you're not speeding up or slowing down. How is that possible? You're accelerating by changing your direction. And we talked about moving in a circle. Who remembers, if you're moving in a circle, which way are you accelerating? Toward the center. Toward the center. Which way is the net force then? Same answer. Toward the center. Ooh, but which way is the velocity? We had this fancy term, tangent to the radius. Tangent to the radius. And then I did a bunch of talking trying to convince you that although you're so used to thinking when you're on a merry-go-round or on an amusement park ride that's going in a circle that you're getting forced outwards, you're not. There's no force pushing you outwards. That's just your own inertia wanting to keep going in a straight line at a steady speed. Instead, you're getting pushed inwards. You're moving inwards. You're accelerating inwards. We did some vector math to prove that. We looked at some interesting videos, but what we hadn't yet got to was the equations. So I wrote here, how do we calculate circular acceleration? There is a lovely proof, but it's a bit long. I'm just going to give it to you. So we're still going to use the letter A as our symbol for acceleration, but I usually use A with a subscripted C for circular. And it's calculated by V squared over R. And hopefully you can already figure out what all those mean. V, that's how fast you're traveling in a circle. That's your speed. What do you think R stands for? Radius. Yeah. Oh, and this does have a squared in it as well, similar to the kinetic energy equation, which also means if you're spinning twice as fast, the force on you is 4 times larger. That's why those amusement park rides that move in a circle have such strong G's, because of that. So, for an object in a uniform or constant speed circular motion, we can say that for an object making one complete loop around the circle, its speed will equal distance over time. Say what? We're going to say this. Speed equals distance over time. I can say that because although there is an acceleration, it's not causing the speed to change. It's causing the direction to change. And that's going to give us our circular speed equation. If you're moving in a circle, the distance is once around the circle. We call that the circumference. Does anybody know what the equation for the circumference of a circle is? 2 pi r. And here is where Mr. Dewick has been a bad teacher. I appropriated a letter in forces. When we were doing tension, I used a capital letter T in forces, and I really shouldn't have. Capital letter T is the symbol for the period, and the period is how long it takes an object to go around once. We also call circular motion periodic motion, and as soon as you get back to where you started, you've done one period, one circle. And unfortunately, there is a situation in your future where there's going to be both tension and the period in the same equation. And usually then, instead of using T for tension, I use F with a subscripted T for tension, which I really should do, and I'm bad. Are both of those on your formula sheet? Yeah, okay. Example 6, an object is moving at 4 meters per second in uniform circular motion. It accelerates at 2 meters per second squared for 3 seconds. Mud, what does A want me to find? It's on your sheet in front of you, too. You can read. Okay. Now you're following along with us? Good. What does it want me to find? Good. What's the answer? Put your calculator away, Garrett. This is the weirdness. Garrett, what did I underline? 3 words. 3 words. Say it again. Final speed is 4 meters per second. Because if you're moving in uniform circular motion, your speed is not changing. But there's an acceleration. Yeah, you know what that acceleration is doing? Changing the direction, not the speed. What's the distance traveled? Again, you might be tempted, don't write this down, you might be tempted to go something like d equals VIT plus a half AT squared. No. The distance is just going to be speed times time, because the speed is not changing. Yes, there's an acceleration, but it's causing the object to change direction. The distance is very simply 4 times 3, it's 12 meters. You'll notice I didn't use that 2. If they had asked me questions involving forces and accelerations, I'd use that 2, because there is a force pulling this object in a circle. And this is where, unfortunately, maybe I've drilled habits in you too good. So you're really going to have to notice when we're moving in a circle, you're going to have to unlearn some habits that I've really pounded into you about velocity and accelerations. So one of the phrases you're going to hear me say often is, hey, what path are we tracing out? A circle. That's to move us into our circular motion thinking. So I have a second equation for circular acceleration. Turn the page. This one is a little more cumbersome, but this one is more useful because it's easier to get the data. I already told you that circular acceleration is v squared over r. And I told you that circular speed is 2 pi r over the period. Now I'm going to stick that in for the v. I'll get this. 2 pi r over the period squared over r. I'm going to combine these two. Then I'm going to put the squared onto there, onto there, onto there, and onto there. I'll get 4, 2 squared. Pi squared is just going to be pi squared. R squared is just going to be r squared. T squared is going to be t squared. And this whole thing is divided by r. Really what that means is one of the r's on the top will cancel that r. This is your second version of circular or centripetal acceleration. 4 pi squared r over the period squared. I'm pretty sure I gave you both on your formula sheet, did I not? This second one is way more useful when we go to Playland. I don't think the Playland field trip is running this year. They haven't announced it yet, but normally when we go to Playland, you can't figure out how fast the ride is zooming past you. You don't know V, but it's pretty easy to time on your smartphone how long it takes to go around once. You can get the period really easily. So we almost always end up using this one to calculate our circular accelerations. So in summary, we have this. A equals v squared over r, or 4 pi squared r over t squared. I use the one with the v if they give me or ask for the speed. I use the one with the t if they give me or ask for the period. Where t is the period in seconds, how long to go around once. R is the radius. And V is 2 pi r over the period. So, bit of a technical comment then on the next page. In circular motion, we have a strange situation. The object is moving at a constant speed, but it's also accelerating. Yeah, that's because the acceleration is changing its direction, not its magnitude. The acceleration vector is actually changing its direction all the time because the center of the circle is in a different direction depending on where you are on the circle. So we have this situation because the acceleration is changing direction, but it's changing. We can't use our constant acceleration equations from physics 11. We have to use our uniform circular kinematics equations, where AC is v squared over r, or 4 pi squared r over t squared, where v is 2 pi r over t, and then d is just vt, or v average times t, if you're going to be really finding a displacement. Example 7. Turn the page. The Earth is currently rotating. I'd like you to imagine that through some cosmic catastrophe, the Earth instantly stops, but all of us on the Earth's surface maintain our centripetal speed. We would go flying into a wall due to our inertia, as though you were in a car that came to a stop and you weren't wearing your seatbelts. You would just keep going in a straight line at steady speed. First question, which wall would we go flying into? The north wall, the south wall, the east wall, or the west wall? In my classroom, by the way, the back of my room points north, the front of my room points south, so that means east is to your left, west is to your right. Which wall would we go flying into? That's north. Behind you is north. Which one? First of all, which two directions might you be tempted to cross out? Okay, I know it's not those two. So the real question is, right now, are you all moving really fast to the east, or are you all moving really fast to the west? And convince me. You're all having to really think here. Yeah. The sun sets that way, but although we said the sun sets that way, it doesn't. It doesn't move. The only way the sun can appear to move from the east to the west when it doesn't move is if we are moving from the west towards the east. We are moving towards the east. So we will absolutely go flying into the east wall. So sorry, Owen and Arsh and Karen, those rows would all dogpile on you. But, how fast would we all go flying? You know what? It depends where you are. So on the equator, how fast would people go flying into the wall? Well, I guess now we're moving in a circle. So we want to find circular speed. And now, for the remainder of this year, we are often going to be using the back page of our formula sheet, the data section. There's a big section where I've given you a whole bunch of data because 2 pi, I think I've given you the radius of the Earth. It's there somewhere, which is what? All over. What's the period of the Earth? 24 hours. That's okay. Can you all get your calculators out, please? On your calculator, can you go 24? How would I convert that to seconds? Times 60 squared. You get 86,400 seconds. That's what I gave you on your data sheet too, right? I think I gave you the period of the Earth. 86,400. It's 86,400. Oh, it's 8.64 times 10 to the fourth. Mr. Dewick, are there not 24 hours in a day? Mr. Dewick, wait a minute. Have we been lied to? All this all depends what you mean by a day. For now, we'll use the one on our formula sheet, which is 8.61 times 10 to the fourth. Okay. How fast would you go flying into the, how fast would Karen and Arsh and Owen hit the, and how fast would all of us dogpile on top of them? I'd kind of like to know. I want to crunch this. Also, you want to figure out how your calculator works with pi. Some of your calculators, you might find you have to type certain things in strangely because the software deals with pi a bit weird. You might get errors if you leave certain characters out or take certain shortcuts. Oh, Zach is reaching for his calculator finally? Good. Y'all get 465.6? We'll call it 466 meters per second. How many kilometers per hour is that? Ooh. People on the equator are not surviving. Well, so follow-up question. Where on Earth would your preferred location be if such a disaster were to occur? Okay. Now, we don't have a permanent settlement on the North Pole because that's ice and it moves, but we do have permanent settlements on the South Pole research stations that are staffed year-round. They wouldn't know anything until their radio calls weren't getting responded to. So, there's your interesting sci-fi movie idea. The rest of the Earth, though, it would be pretty awful because everything would keep moving at that speed, including the wind. So very rapidly, you would have winds of 1,676 kilometers per hour. The air would keep going. It would strip the Earth pretty bare, pretty quick. Oh, now the wind would be this churning ablative mass of trees and debris and rocks. It would be like the worst sandpaper you can ever imagine. It would be quite interesting. Mr. Dewick is now going to mention a little bit about angular momentum, and I'm going to show you some cool demonstrations as well as an addictive toy, and then I think I need to talk about what is meant by 24 hours. What's your homework? Number 1, number 2, number 3. You'll need to use your data sheet for all of those, so that'll be the back page of your formula sheet, but all the information that you need to find periods and radii and all there. Number 4, I'm not going to circle, but let's talk about it. It says, explain how the spin cycle on a washing machine works to partially dry clothes. Specifically, if you were looking down and you saw the spin cycle in slow motion, if this was a drop of water right there, what path will it trace? Okay. Once it leaves, what path will it trace? Okay. A lot of people think, oh, the water flies out that way. No, it does not. The water would fly out and hit there. A drop of water would hit the edge of the washing machine there. A drop of water. Remember, I showed you the video of the kids on the merry-go-round with the motorcycle, and we saw they did not fly straight out. They flew tangent to the radius. So we've talked about number 4. 5 is good. 7 is good. I skipped 6. 8 is good. 9 is good. 10 is tricky, but nice review. So, if we look at number 10, a student is on a Ferris wheel, and the Ferris wheel moves in a circle radius 5.8 meters with a period of 10.5 seconds. At the bottom of the path, the student is 1.7 meters above the ground. I would probably label this. There's 2 situations. A student, first of all, find the centripetal speed of the student. And then, what does it say? The student drops their hot dog at the top of the ride. And they drop a water bottle at the bottom of the ride. Find the range of each of them. Both of those are the same physics as launched horizontally from a cliff. So I would do it, right? You're moving horizontally at the top for a split second. You're moving horizontally at the bottom for a split second. So I would do a t-table for each of them, and you should be able to handle it just fine. We won't do the experiment. Don't drop things from Ferris wheels. That's not nice, but the physics there is good. Okay? 11 is good. 12 is good. 13 is good.